Hello, my name is Milena, which I'll be presenting on behalf of the team that worked on paper titled Ultimate Strands of K Joints in Lattice Structures Composed of Circular Hollow Sections. Specifically, this paper deals with the application of appropriate diagrams and nomograms for the static design of members of welded K-gap joints in lattice structures. Throughout the presentation, the calculation steps in accordance with the relevant Euro codes will be shown in a particular example. A comparison will be made between the calculation procedures given in the first and the draft of the second generation of VN 1993 Part 1.8. At the end of the presentation, changing the position of members will also be considered. So let's start with the example. The material, the geometry of the joint, and forces in members are shown here. The data will again be shown along with the calculation. In order to verify that the structure will be able to resist the assigned forces, we have to verify the design buckling resistance of compression members, the design resistance of tension members, and the design resistance of the joint of the lattice structure. Here, only the first and last criterion represent the relevant criteria, so we'll be considering only these two criteria. In order to adopt the compression members, we'll be using buckling resistance curves. This is the formula for the buckling resistance of compression member. This formula comprises two parts. First part is the reduction factor. This factor depends on the buckling length, the yield strength of the material, and the imperfection factor. It's a variable and describes the buckling effect. Second part is the design resistance to compression, and it's a constant for a particular section. The buckling resistance curve can be constructed as a function of only the buckling length, but that implies that all the other parameters, yield strength, imperfection factor, section dimensions, have to be previously specified. Since we can adopt these parameters in many different ways, we can construct quite a number of buckling resistance curves, but the good side is that we can use a specific set of buckling resistance curves plotted on the same pair of axes in order to quickly adopt the appropriate section. And I'll show that in our example. I want to adopt the chord, and the specified steel grade was S355. The force in the chord was around 250 kilonewtons, and the length of the chord 280 centimeters. Let's assume I have buckling resistance curves already constructed for both hot finished and cold formed circular hollow sections of 3.2 and 4 mm wall thicknesses. On the horizontal axis of the first set of curves, I mark the buckling length of the chord and draw a vertical line from the marked point. On the vertical axis, I mark the force in the chord and draw a horizontal line from that point. I mark the point of intersection of these two lines, and only the sections that fall above this intersection point satisfy the buckling criterion and may be used in the structure. The most rational section is the one closest to the intersection point, and in this case, it's this hot finish circular hollow section with a 0.89 utilization ratio. We can repeat the procedure with the other set of buckling resistance curves, and in this case, if we use a hot finish circular hollow section, the most rational section is this one with a 0.72 utilization ratio, and if we use a cold form circular hollow section, the most rational section is this one with a 0.89 utilization ratio. We can repeat the evaluation with the braces. Now, I won't be explaining that again. At the end of this first check, you can see the sections we adopted. Now we have to check the design resistance of our joint. This is a K-gap joint configuration with its geometrical parameters, diameter and thickness of the members, the included angle between the braces and the chord, the gap, the eccentricity of the joint. Here the subscript denote the members, so we use 0 for chord, 1 for compression, and 2 for tension brace. Our subject is a welded joint, and determining the design resistance of this joint is actually quite complicated, so for that reason, to describe its design resistance, we use some empirical formulae derived based on some simplified analytical models combined with experimental evidence. There are several failure modes of K-gap joints, but if we follow the usual recommendations when adopting their geometry, we can reduce the failure modes into two possible cases: plastification of the chord and chord punching shear failure. Moreover, if we follow these recommendations, the governing failure mode is the plastification of the chord, so we just have to make an additional check for chord punching shear failure. This table shows formulas and limitations for determining the design resistance of a K-gap joint according to the first generation of PN 1993 Part 1.8. The formula for chord plastification can also be shown in this general form, and these three functions only depend on the geometry of the joint, and function here, factor Kg here, joins the functions of gamma and G prime. Function of M prime depends on the level of the stress in the chord, and factor Kp corresponds to this function. It depends on the ratio MP, which is the ratio between the chord's so-called pre-stress and the yield strength of the chord divided by the partial factor. The pre-stress in the chord would be the stress in the chord we get when we exclude the portion of the stress produced by the horizontal brace load components. Note the subscript here. The subscript is 1, which means that we describe the design resistance of our joint as the design resistance of the compression brace. And that means that the design resistance of the compression brace depends on its buckling length, but also on the level of the stress in the chord. The higher the level of the stress in the chord, the lower the design resistance of our joint is. We had to determine the geometry of our joint, so we adopted the gap so that the eccentricity equals 0, and we adopted the included angle between angles between the braces and the chord as 45 degrees. We named that joint an ideal K joint. And now we have to consider both of the criteria for the design resistance of our brace, and for that reason we can construct a nomogram. We constructed a nomogram for this combination of sections we adopted in our first step. And for example, if the value of the MP ratio is 0.6, we draw a horizontal line from this point, and at the intersection with the vertical axis, we can read out the value of the design resistance of our joint. At the intersection of these two lines, there's a point which corresponds to a certain value of a buckling length, which we call the limit buckling length. That is the length of the member for which both of the failures occur simultaneously, and if the length of the member is lower than this value, then the relevant criterion is the plastification of the joint, and if it's higher, then the relevant criterion is the buckling of the compression brace. Our brace has a buckling resistance of 51 kN, which is higher than the force in the brace, but in order for simultaneous failure to occur, we need to have the value of the NP ratio to be 0.2. Unfortunately, this value is 0.45, which means this combination of sections doesn't satisfy the second criterion, and we need to find an appropriate combination of the sections. This table shows the design resistance of our joint for a combination of the brace we adopted in our first step and some different chord sections, and for different levels of stress in the chord. These combinations are in accordance with the geometry limitations Eurocode gives, and if we use this data, we can construct a nomogram from which we can directly check if our brace satisfies both of the criteria. So, for example, if we choose this chord, we can get the design resistance of our joint to be 72 kN, which means that this combination of sections satisfies both of the criteria. This table shows formulas for determining the design resistance of a K-gap joint in accordance with the draft of the second generation of PN 1993 Part 1.8. This long expression can also be shown in this general form. Actually, if we know all the geometrical and material parameters of our joint, the only variable is this QF function, chord stress factor, which depends on now the maximum level of the stress in the chord, but also on the type of the joint. And in this figure, you can see the difference between the nomograms constructed for the first and the draft of the second generation of PN 1993 Part 1.8 for this combination of chord and brace. According to the draft, the value of the design resistance of our joint is 52.2 kN. So compared to the recommendations given in the first version of Eurocode, there's a 10% increase in the design resistance of the joint. Up until now, I have been analyzing an ideal K joint, but applying the nomogram for different positions of members comes into question. In order to be able to apply the nomogram for different positions, we need to vary the gap and the included angles between the braces and the chord. For different values of the included angles, we have to multiply the design resistance of the ideal K joint with this factor. Different values of this factor are given in this graph. for the included angles between 30 and 90 degrees. So this first graph is the first auxiliary graph. And now if we vary the included angles, or if we vary the eccentricity of our joint, we also vary the gap. And the expression given in the draft of the second generation is convenient because it separates functions of gamma and g prime. Therefore, we can independently analyze the influence of the function of g prime, that is, the influence of the change of the gap on the overall resistance of our joint. This influence can be shown by reduction values nominated as KRG. These values directly depend on the ratio between the actual gap between the braced members and the gap for the ideal K-joint. If this ratio is higher than 1, the eccentricity is positive, and if it's lower than 1, then the eccentricity is negative. Considering the limitation Eurocode gives for the positive and the negative eccentricity, and also for the minimum gap of our joint, we constructed the following graph for different diameters of our chord given in our nomogram. This graph shows the different values of the KRG factor depending on the G to GI ratio. And this is the second auxiliary graph. Actually, the function of G prime also depends on the thickness of the chord, but this influence is very small. So, for example, for this chord section, if we show the values of the KRG factor depending on the thickness, we can see that this difference is very small. So for any thickness, we can choose the value of the KRG factor that corresponds to, let's say, the mid thickness. At the end of this presentation, we can conclude that the aim of the paper was simplification of the method for the design of members of K-joints and lattice structures composed of circular hollow sections. We used buckling resistance curves in order to adapt our compression members. These curves also give an insight into the utilization ratio, in which way they can help us rationalize the structure. Nomograms, on the other side, imply the way the limit state is reached, and they provide us, help us directly check if our combination of braces and chord is appropriate. At the end, if our joint isn't an ideal K-joint, or the eccentricity isn't 0, or the included angles aren't 45 degrees, or both, we can use the nomogram for the ideal K-joint along with the auxiliary graphs that take into account different positions of members. And this was only one case, we discussed only one case, but also we can construct similar nomograms for other types of joints and other hollow section shapes. And that was all from our team. Thank you for your time.